last paper, that is MCH-004 paper, and we have already discussed uh, your block 1 related to your general electrochemistry or electroanalytical methods, followed by potentiometric analysis, in which we have studied pH metry, and in the latter part we have discussed conductometric titration or conductometry, in which conductometric titration was also there. And yesterday we have studied the concept of electrogravimetry and the electrogravimetry technique, and today we will discuss about voltammetry as well as polarography techniques. So these are all advanced study on electrochemistry generally, and this is very much related to some of the parts of physics as well as electrical engineering part. And let's have today's discussion on voltammetry as well as polarography. So I'm sharing my screen with you now. I think this is visible to you all, polarography and voltammetry. Is there any problem or is it visible clearly, students? Anyone please reply. Is it visible?
Yes, sir. Yes, sir. It is properly visible.
Okay, thank you. So this electroanalytical method, the name is voltammetry. So voltammetry means is related to voltage. What is voltage? It is the cell potential or the potential difference occurred during electroanalytical methods. Electroanalytical methods. So we have this part is in your unit 7, that is voltammetry, and in this part we will have some objectives followed by electrode and its processes, and different type of voltammetric methods such as direct method, linear sweep voltammetry, sampled DC polarography, SDCP, hydrodynamic voltammetry. This is HDV, and we have some pulse method like normal pulse method, differential pulse voltammetry, square wave voltammetry, cyclic voltammetry, stripping method, anodic stripping voltammetry, cathodic stripping voltammetry, adsorptive stripping voltammetry, then SC methods such as alternating current methods such as voltammetry instrumentation, and in the end we have summary. Actually, these are very technical engineering related topics, and in our BSc or PG level, in my time, I have I have not gone through details of these things, and we have in our syllabus we do not have these things in elaborately. We just have a brief knowledge on these parts, but IGNO prepared very good material for you guys, that each and every section of this voltammetry explained very beautifully, and if you wish to understand the things, and this PDF is very much helpful than my PPT. Okay, so let's go through this PDF first, and if any problem arises, then we may see our PPT. that what are the objective of this part. We have to define voltammetry, what is voltammetry, and we will discuss the electrode and processes of voltammetry, discuss the direct current method in voltammetry, explain the pulse methods, explain anodic, cathodic and adsorptive stripping methods, discuss the alternating current method in voltammetry, name the instruments involved in voltammetry, that is the instrumentation part, and what are the suitable method for voltammetric analysis of particular sample. So we will have a broad knowledge on voltammetry through this unit. So what are the different electrodes and processes involved in voltammetric analysis? So by from its general name, it is given to a group of electroanalytical method in which current is measured as a function of applied voltage. So here current means in ampere. So current is determined, that is the unknown parameter here, and which is measured as a function of the potential difference arises due to polarization of the indicator or working electrode, working or in working electrode. That is the mainly working electrode at the cathode, in which the metal is supposed to be deposited like our electrode on a apparatus. Then it is followed by a very developed technique, that is known as polarography or polarographic method, which is developed by Herovsky. It is a particular type of voltammetry. So it is just parallel to voltammetry method, in which dropping mercury electrode DME, it is used as a micro electrode. So voltammetry include all technique in which the current potential measures are made at a stationary and fixed electrode. So just remember one thing, in voltammetry as well as in polarography, we will determine the current as a function of applied voltage. So here we have some electrodes generally used as working electrodes. Then they are mercury dropping electrode, that is hanging mercury HFD, static mercury dropping electrode SFD, thin mercury film electrode TFFE, then glass carbon electrode GCE, carbon based electrode CPE. So these are some of the electrodes which are used as working electrode in voltammetry as well as in polarography. Because is a version of your voltammetry, right? So let's have some processes like these are used for the quantitative analysis of trace metal at micro level, and in addition to this aspect, this technique is quite versatile for research purposes in the field of redox, electron transfer mechanism, adsorption, corrosion, then new electronic processes, then production of new types of batteries that can store large quantities of electricity. So these are some applications or processes for voltammetry. So these are the electrodes, that is working electrode generally used in voltammetry or polarographic techniques. And this first one is the a Dix electrode. This is a Dix electrode in which the conducting disc is here. This is just a plastic, that is Teflon, and this is a wide lead. So this is a means it is a lead wire which is used as the working cathode or working electrode. Similarly, this is dropping mercury electrode, that is DME, in which this is the mercury and this is a mercury drop here, means it is in hanging position. That's why this is known as hanging mercury drop electrode. That means it is HDME, hanging mercury dropping electrode. Then it is followed by the C is our a dropping mercury electrode. The second one is this one, mercury hanging dropping. The third one is dropping mercury electrode. So in which what happen, there is a mercury drop is here, and it is in a capillary. So this is known as your dropping mercury electrode, DME. And at last it is your SMDE, that is static mercury dropping electrode, and in which there is a steady flow of mercury drop from this electrode, which is very much complicated, and this part contains the mercury, and mercury will be flow through this capillary, and we have some instrumentation parts like solenoid here, then a plunger here, then guide pushing, compression spring. So these things are here, and this is very important that capillary is placed here, and here what happened, there will be static flow of mercury. So this is known as static drop, mercury dropping electrode. So these are some of the examples of your working electrode in voltammetry or in polarography. Then these are the common voltammetric techniques, like your if the current is direct current, then we have a DC polarography, we will discuss in unit 8. Then linear sweep voltammetry, that is LSV. Linear sweep means it is it will linearly flow. Then sampled DC polarography, then hydrodynamic voltammetry. So voltammetry and polarography both are goes parallel to each other. Then we have pulse method. In plus pulse method, we have normal pulse voltammetry, the differential pulse voltammetry, square wave voltammetry, cyclic voltammetry. Then it is followed by stripping voltammetry, then anodic stripping, cathodic stripping, and adsorptive stripping. Then at the end we have alternating current. So these are the basic four types of voltammetry, and under which different type of voltammetry as well as polarographic techniques are there. So let's discuss one by one. That direct method. So the first one is your linear sweep voltammetry, because DC polarography is in our unit 8, that is in our next unit. So this is the simplest type of voltammetry, also called linear sweep voltammetry, that is LSV. In this technique, the potential of the working electrode is varied linearly as a function of time and current. It is very simple method, that the potential will vary linearly as a function of time and current. The scan rate are relatively low, that is less than 5 millivolt per second, which allows the moment of press analyte to reach the electrode surface, so that the electrode is always in equilibrium with the bulk solution. So this is very much a simple technique, in which there will be steady or linear flow of the analyte to reach the electrode, and here the potential of the electrode is linearly varied as a function of time and current. So let's have a reduction reaction. I told you that in electrochemistry or electroanalytical method, always the according to the latest rule of IUPAC, always we should take the reduction potential for the calculation of the E cell, that is EMF of the cell. So that's why we always should write the reduction equation, that is the gain of electron. So it is A plus E electron, that is A plus electron gives rise to E. So here let the standard reduction potential, that is E0, is 0.00 volt, which obey Nernst equation. So here E is the potential of working electrode, so E is the standard reduction potential of A. Here it is written E0 is the standard reduction potential of A, and where we can find the standard reduction potential, we will find their values from electrochemical series, that is ECS, right? Electrochemical series. There is a table is there. Fluorine is at the top, lithium is at the bottom, and then fluorine has the positive value of maximum positive value of reduction potential, that is plus 2.97, I think it is volt. Then lithium has the least reduction potential, standard reduction potential, that is minus 3.05 volt. So that's why fluorine is the uh, um, fluorine has the highest or maximum reduction value, then followed by lithium, and it is hydrogen is there at the middle, which has the standard reduction value of 0.4. Okay, so here it is written, if a solution containing only A is taken in a cell and applied potential is about 200 millivolt is applied, then a minuscule amount of current will flow to convert a small amount of A to B, so that Nernst equation is obeyed. The amount of current increases as the potential approaches E0. So when E becomes equal to E0, then concentration of B is equal to concentration of A. So here at electrode surface, or in other words, at E0, half of the total A reaching the electrode is converted to B, and so that the current is halfway to its limiting current. So when what happen? The condition is applied here when the net cell potential equal to the standard cell potential. At this condition, we can say the cell is in equilibrium. What is equilibrium? The concentration of B equal to concentration of A. So this situation arises when we will have the half of the total A reaching the electrode is converted to B. So this is known as the half. This is known as the half wave potential. Also, it is also called as half wave potential. And here there is potential versus time graph is here. It is very much linear, and this is the slope, and that will be del E by del T. That is Y by X. Then we have, this is the diffusion current ID. It is directly proportional to concentration of A, and we have some proportionality constant here. So this is ID equal to K into C. Then we have one graph is plotted here, that is working electrode potential. Generally it is mercury electrode, that is dropping mercury electrode DME, versus the current recorded. Okay, then we have the plot is just like this, and this is the half wave potential, that is E half. This is the half wave potential, and this is denoted as E half, right? So then polarography determination with higher sensitivity can be achieved with the ratio of IF by IC. What is IF? It is the Faraday current, and what is IC? It is the condenser current. So the two parameters are again introduced. That is the Faraday current, means it is, what is one Faraday? One Faraday equal to 96500 coulomb. Okay, so convert it to current by multiplying it with I into T equal to Q. So it is IF by IC is another ratio, that is it has a significance of higher sensitivity. If the ratio is high, then the sensitivity will be high. Then this modification give rise to sample DC polarography and pulse methods. So in normal DC polarography, the electrode area is not constant, so just go through these things. Then we have sampled DC polarography. In this technique, instead of recording the current continuously, it was sampled for a 5 millisecond period just before the drop falls. So here always remember the mercury from the electrode will flow, and it will fall drop by drop, and depending upon the time period it taken, we can determine the current as a function of potential. This will be the principle. That is the that is we recording the current continuously. It was sampled for a 5 millisecond period just before the fall drops. Before sampling period, the recorder was maintained at its last current level by means of sample and hold circuit, and this is the LSB, okay, the linear sweep voltammetry. And the major advantage of current sampling is that it substantially reduces large current fluctuations due to continuous growth and fall of the drop at dropping electrode. So this is the step figure that is indicates this is sample DC polarogram. This is voltage versus current, again E versus C, and we will have this type of graph, and this is the midpoint of this plot. So this is known as the half wave potential, that is indicated as E half. Okay. So similarly, when LSB, that is linear sweep voltammetry, in which the solution or electrode is kept in motion, this is very important. If LSV is in solution or electrode in which it is in motion, it is known as hydrodynamic. So dynamic means it is in some kinetic energy is there. So how this kinetic energy will arises? This is from this motion of the solution or the electrode. So we have hydrodynamic voltammetry. This one. So in hydrodynamic voltammetry, current is measured as a function of potential applied to a solid working electrode kept in stirring solution. That means here what happens? One extra mechanical stirrer is there, which generate a motion or dynamics in the electrode. So this is known as hydrodynamic. So linear scan profiles are used while the solution is in motion towards electrode. The cells, there are three cells are generally used in hydrodynamic. These are the working electrode, like in our electrode battery. Then we have working electrode. We have mercury coated electrode, that is your mercury electrode. Then a reference electrode is our standard chemical electrode SCE, and we have counter electrode, that is the anode, and this SCE is the reference, and working electrode is the cathode. So working electrode means it is mercury coated with coated electrode. The reference electrode is to the role of reference electrode is to maintain the potential at constant potential, to maintain the constant potential in the cell. So that's why reference electrode is used, and the counter electrode is just the anodic part of this cell. So the current in the cell between the working electrode and current electrode, the electroactive substance undergoing electrode reaction at microelectrode is brought to the electrode by three modes. So what are the three modes? This will be migration, convection, and diffusion. These are three modes by which the active substances undergoing electrode reaction at a microelectrode. First one is migration will be there, migration of the charged ions from that substance under the influence of electric field, that is due to attraction of electrode that has a positive and negative charge. So the first step is the migration of the charged ions of electroactive substance in applied electric field. It is followed by convection, that is stirring, that is mechanical stirring will be there, or vibration will be generated through stirring, then followed by the diffusion. Diffusion due to concentration gradient, that is concentration per volume, and the concentration gradient established near electrode during the reaction. So these are the three steps or three denotes how the electroactive substance undergoes electrode reaction. First one is migration. This is in hydrodynamic voltammetry. The first one is migration of charged ions in applied electric field, followed by stirring, that is convection, and followed by the diffusion, that is concentration gradient. Then we have one mathematical equation is there, that is I equal to NFAD by delta into CA, where CA is the concentration, N is the number of electron transfer, F is the number of Faraday, or Faraday constant, that is 9654 double zero coulomb. Then A is the area of the electrode surface, and then D is the diffusion coefficient. Then I is, as we know, I is the limiting current or maximum current, and delta is the thickness of the nonce layer. So just remember this equation of hydrodynamic voltammetry. So this is the instrumentation part. Here we have the working electrode here. That is working electrode is coated with mercury, then followed by the standard calomel electrode. The role of this electrode is to maintain the potential, that is a constant potential, to maintain the constant potential, because in voltammetry we determine the current as a function of potential. So that's why the role of a CE is to maintain the constant potential. Then this is counter electrode is there. This is the counter electrode, and the SHE have the salt bridge, and this is the stirring bar, means it is the magnetic stirrer. That is the this is the convection, that is the stirring part, which give dynamics or motion to the electroactive substances here. Here it is also written that stirring is accomplished using a magnetic stirrer. This is magnetic stirrer. But in some other cases, the electrode is rotated through a constant high-speed solution, thus providing a stirrer action. Or mechanical stirrer may used, and this is all about your hydrodynamic voltammetry. Okay, then let's have some pulse methods. The sensitivity of LSV or polarography is limited by charging current, which is large initially in the drop life, the slowness, inconvenient apparatus, and poor detection limit of LSV or polarography were the reason for its decline. The sensitivity of these two methods is improved by pulse method by about 6.5 times. So why pulse method is needed? Because the methods, that is linear scan or linear sweep voltammetry or polarography methods, these are less sensitive and inconvenient apparatus these have. So due to less sensitivity, we may use another advanced technique, that is a pulse method, which is about 6.5 times more sensitive than these two. The current in this method is measured at a time when the difference between IF and interfering charging current is large. There are four important pulse methods are there, such as normal pulse polarography (NPP), then followed by differential pulse polarography (DPP), square wave voltammetry, then cyclic voltammetry. Then what is NPP? Normal pulse. In this technique, the potential is altered by using square wave potential pulses and is applied only briefly for about 50 microseconds before each current measurement. The data obtained have the same shape of LSB and the sensitivity is increased. The dropping mercury electrode is held at the initial position until there are only about 60 milliseconds left in the lifetime of the drop. Thus, very little electrolysis and depletion occur during the last 15 milliseconds. So before the expiration of the pulse time, the current is measured. Each new drop is stepped up to a greater potential and is measured after about 40 millisecond delay. A sensitivity important improvement of approximately 3 times is observed. So here it is just related to the timing. That is how the drop or the dropping time varies with current, or how the dropping time varies with current at constant potential. So at a different time interval, that is at 60 millisecond, 15 millisecond, 40 millisecond, we will have the dropping time followed by the respective currents recorded in the ammeter. Then these things are there in normal pulse polarography. And in differential, a still greater improvement is reached by using programming wave. This is just a computerized thing are here. There is programming wave as shown in 7.6. So these are all computerized. Okay, so these the technique like TAST, NPV, SCV, DPP, differential pulse polarography, SWP, SCP. These are some potential plots, current responses, working, what are their working electrode use, then what is the LOD. So this is limiting current density, LCD. Okay, so this is ID. So we have these things in computerized programs. That is programming waves are there. The millivolt pulse is applied for 50 millisecond, and these things adjust the differential between the normal pulse polarity and the data is obtained by making it standardized. That is 50 millivolt in for 50 millisecond, but the differences will be arise, and this will be the differential pulse polarity. The difference in the current is plotted. It is written. The difference in the current is plotted, resulting in peak shaped curve. The top of the peak corresponds to E half wave potential, and the height of the peak will be the concentration. So these things will be there. So this is the half wave potential, and the height will be the concentration. This will be the total concentration. The peak current is differential pulse photography increases linearly with the concentration of the analyte. So these things are very much common that when the concentration is more, the differential current will be more, because ID is proportional to concentration of A, or it is equal to K into Ca. Already we have discussed. Then this equation is there, that is peak current IP n square F square by 4RT into A Ca del of Ea root over of d by pi into dp. Just try to remember this equation only, and for your differential pulse polarography. So where Ip is the peak current, N is the number of electron transfer or exchange, F is Faraday constant, R is universal gas constant, T is temperature in Kelvin, A is surface area, Ca is the concentration of analyte, then Ea is the pulse amplitude, the differential pulse amplitude. Then it is D is the diffusion coefficient, pi and dp will be the pulse duration. That is in differential, it is 50 milliseconds. This is dp. And Ea, what is Ea? And Ea will be your 50 millivolt. This is 50 millivolt. This is 50 millisecond, and you have to put the according to the number of electron exchange. We have different IPs for differential pulse polography. Okay, so here remember it is delta EA is 50 millivolt and TP pulse time it is 50 millisecond. Okay, and the rest things we will have depend on the, because the variable here is n, that is number of electron transfer. Then we have the last line, the detection limit for the determination by this technique is similar to square wave polarography at 10 to the power minus 7 to 10 to the power minus 8 mole per liter, but for irreversible reaction it is lower. So when the detection time for this technique, that is differential polarography, is similar to the square polarography. So let's have the next part, that is square wave polarography or voltammetry. In this type, the advantages is with respect to the normal pulse polarography and differential pulse polarography. These have high sensitivity, great speed, and low detection limit. So these three advantages are there, that in low concentration it can detect, its speed is very much high, and sensitivity also high. The entire voltammogram, like the total cell, it is known as, now it is known as voltammogram. Like a chromatogram we have discussed in MCH-2 paper. From chromatography it is chromatogram. This is from voltammetry, the cell is, or the system under investigation or system under study, it is known as voltammogram. It is obtained in less than 10 microsecond. It is use a potential wave, that means the time is very less. When time is less, the speed will be great speed, a greater speed. It uses a potential wave from similar to one used in DPP, differential plane polarography, and the entire potential sequence is applied during the lifetime of the single drop. That means one single drop of mercury lifetime, where we will determine the potential sequence. This can be used with the dropping mercury electrode and HMDE also, that is hanging mercury dropping electrode. We can use both, either of the electrode for this purpose as the working electrode or cathode. The excitation signal in this technique is obtained by superimposing the pulse shown on the staircase signal, the length of the step. Just go through these things. Okay. So these are just the instrumentation parts are written here. Then we have the equation, that is IP. This is for your square wave. So for square wave, IP is equal to Kn square D to the power half delta EA into CA. And here IP is the peak current, K is constant, N is number of electron exchange, D is diffusion coefficient, delta EA here is, it is equal to pulse amplitude, and Ca is the concentration of the analyte. So these are the things you should remember for your examination. And here just see here, the magnitude of pulse is 50 millivolt. So here delta EA we may put it is 50 millivolt. Okay. So then cyclic voltammetry, that means the a cyclic type system will be there, and this is this graph. It is just a continuous graph like a cycle. So CV is an attractive method for teaching of a number of concepts in electrochemistry. In brief, it is perhaps the most versatile electrochemical technique for the study of electroactive species. Electroactive species means these are either charges are present. The effectiveness of cyclic voltammetry results from its capability for rapidly observing the redox behavior over a wide range of potential. It is very important. That is rapidly observing the redox behavior. That means a reaction where oxidation and reduction took place simultaneously. So in this type of cyclic voltammetry, we will have the redox behavior of the electroactive substance over a wide range of potential. And the voltammogram is similar to conventional spectrum in that it conveys information as a function of energy scan. And in spite of the wide application, this technique is not generally well understood as compared to the other instrument techniques such as spectroscopy and chromatography. So here we will determine or observe the redox behavior with as a function of potential. Okay, so fundamentals of cyclic voltammetry, it consists of cycling the potential of an electrode that is immersed in an unstirred solution. That means no movement or motion is there, then no dynamic phenomena is here. This is unstirred of electroactive species, and then measuring the resulting current, that is ID. The potential of this working electrode is controlled versus a reference electrode such as SC, saturated or standard calomel electrode. So this potential is controlled with the help of a reference electrode. So here also three types of electrodes are used. That is, one is working electrode, reference electrode, and counter electrode. So, or the reference electrode, we may use the silver plate electrode. This may be used. The controlling potential which is applied across the two electrodes can be considered as excitation signal. The excitation signal for cyclic voltammetry is a linear potential scan with a triangular waveform. This is just a triangular waveform like plot is here. This triangular potential excitation signal sweeps the potential of the electrode between two valves. Yes, two valves, sometimes called switching potential. So this is just sweep from one to another. This is switching. The excitation signal in figure 7.9 causes the potential first to scan negatively from 0.80 initial potential. This is a starting potential, 0.80 initial potential, and the scan rate reflected by the slope 50 millivolt. This is the scan rate, and a second cycle is indicated by the dotted lines. Single or multiple cycle can be used. So this is just a cyclic type plots will be there, and this will be 0.80 is the initial. Then with time the potential will decrease, and again at a certain maximum decrease it will again increase. Then this cycling will go on. So these things will be there. Then we have some example of iron 3 cyanide versus iron 4 iron plus 3 6 cyano, the hexacyano, with iron 2 hexacyano 4 minus. And here platinum electrode area is 2.54 mm square, and the initiated potential is 0.8 volt, and we have the concentration of 1 molar potassium nitrate. And we have the analyte, that is potassium ferricyanide, that is 6 micromolar. So these things will be there. Then the reaction will be, and we'll just read these things, that how much concentration, how much potential, how much time is set in the in this part, that is cyclic voltammetry, and followed by what are the reactions, that it is ferric to ferrous. That means it is reduction again, that is plus 3 to plus 2, it is again reduction happen with liberation of one electron. Then the reaction will be sorry, the right, the equation will be Nernst equation. This will be the E cell the net cell potential, it is equal to standard reduction potential of iron 2 to 3 plus 0.0591 by n, and here number of electron transfer is 1 because Fe3 plus to Fe2 plus is 1 log concentration of ferric by concentration of ferrous. So by putting all these values, we have the cell potential, and we have one mathematical reaction related to cyclic voltammetry, that is a Randless Sepsic equation. This is for the fast cycle. Okay, then the peak current in ampere it is 2.686 10 to the 5 n 3 by 2 a d half c 0 v to the power half. So ip is the peak current, n is the number of electron exchange or in stoichiometry, a is the area, d is the diffusion coefficient in centimeter square per second, then co is the concentration, and v is the scan rate. So these are the things. Then we have IPC by IPA equal to 1. Just as IP is proportional to the concentration, the relation to concentration is particularly important in analytical application and is studied for electrode mechanism. The value of IPA, IPC should be identical for a simple reversible coupling. So these are the things there. Then many more mathematical equations are here. That is again E0 equal to EPA plus EPC by 2, EP delta EP equal to these things. Just it is from your Nernst equation. Okay, just remember in cyclic voltammetry you must write this conversion, that is Fe3 plus to Fe2 plus reduction, and followed by the the potential difference of 0.059 volt, because one electron gets exchanged, so that's why there will be difference of 0.059 volt. Then here the criteria for reversible system, then quasi reversible, then total irreversible. So this is when it is reversible, then this is 0.0591 by NB, and if it is quasi means semi reversible. If it is IP increases with uh, this is the what is V? V is the rate. Rate means it is the scan rate, right? So scan rate per half. So these are the things you should follow that uh, by following that equation. By following that equation, this is the equation. This one, IP is equal to this n to the 3 by 2 a d half co d half, and these things will be can be interpreted. Okay, then we have the instrumentation part. In instrumentation part of cyclic voltammetry, we have the cell is here, and these have this is the reference electrode, and this is the working electrode, and this is the counter electrode. Three electrodes are here, and the reference electrode is generally standard or saturated calomel electrode, or saturated silver chloride electrode. Then it is working electrode. This may be mercury coated electrode, and one counter electrode, that is the oxidation half cell or the anodic part, and there will be cathodic part. Then it is for the working electrode, reference electrode, and the counter electrode is known as auxiliary electrode also. So this is just connected to the potentiostat, which maintain the potential at constant potential. Then this is the wave generator. Wave generator means this is the some type of vibrations are generated, and these vibrations are recorded here, and then this is current to voltage converter. Then this is connected to a computer system, and from that we can have the related graphs or plots. Then we have stripping methods. What are the stripping methods? Now, stripping voltammetry is the most sensitive electrochemical technique for the quantitative analysis of quantitative electroactive analyte, which oxidizes or reduces reversibly at a solid electrode or form insoluble species at the electrode surface. So there are two steps of stripping method, that is analyte of interest is electrochemically deposited on working electrode. So this is just same as the electrogravimetric method which we have studied yesterday, by controlling the potential through a register. Then a reverse potential seal or stripping step is applied, in which the deposited analyte is removed from the electrode. So there are two steps are here: that deposition of the electrolyte on the working electrode, this is the first step, and it is followed by the reverse potential or the stripping step is applied, in which deposited analyte is removed. That means it is deposition and removal, both the things will be there. So this is undergoes your stripping method. So this is of three types: anodic, cathodic, and adsorptive. In anodic part, what happened, the in this technique, in this technique um, is to determine the trace amount of metal ion that can be pre-concentrated at an electrode by reduction to the metallic state. The microelectrode behaves as a cathode during the deposition step, and as an anode during the stripping step, with the analyte being oxidized to the original form. So this is just the reverse process, that in the deposition step, the electrode which acts as cathode is converted to anode in the stripping step. Stripping step means it is a removal of the deposited electrolyte. For example, when copper 2 plus gets deposited in hanging mercury electrode, then the cell reaction will be like this: copper in aqueous medium gain 2 electron, and which will give copper, and it is deposited on mercury electrode. And this is the working electrode or the cathodic part. Then what happened, this copper and mercury formed one amalgated. That means copper is amalgated with mercury. This step is basically pre-concentration step, and in the next step stripping will be there. In stripping we will have 1 to 30 minutes of, after 1 to 30 minutes of deposition, we will have the second step, that is the stripping step. In stripping step, the copper which gets deposited in on mercury electrode gets detached or removed from the mercury, and it again goes back to the solution state, that is copper in aqueous medium. Then we have, and the current during this step is monitored as a function of potential, giving rise to voltagram. So the second step, the current is measured at constant potential, the peak current of which is proportional to the analyte concentration. This technique is sensitive to experimental conditions like area of mercury film electrode or size of the mercury drop, deposition time, resting time, rate of stirring, and scan rate. So these factors will affect the current at constant potential. If properly controlled, this method can be very sensitive and accurate, and can be used for the metals that can be amalgated. So this is just a pre-concentration step, means it is deposition, that is step 1, followed by the removal or removal of the deposited metal from the mercury electrode. This is the removal, or this is E clean, and where this is the potential, and this is the current, and we have current, potential, as well as potential time graph here. So this is the potential drop, and this is the current with potential, and this is the instrumentation of the stripping voltammetry. And here the standard electrode or reference electrode uses silver chloride reference electrode. Carbon rod is used here, and this is the working electrode, and there is a copper foil. Okay, there is a button o-ring, nitrogen gas for your inert atmosphere. This is the setup of your stripping voltammetry, and these are the in this is the anionic. Okay, so the equation will be ip equal to k n 3 by 2 d half c m h g mercury d half r square DSCE. Then it is again reduced to IP equal to Kn square AP AF CM mercury VT then SE. So what are the things? IP is the peak current, N is the electron transfer, K is the proportionality constant, D is the diffusion coefficient, Cm is the concentration of the metal in amalgam. This is very important. Here it is Cm, that is metal in amalgam, concentration of metal in amalgam. Then A is the area, V is the scan rate, and TSC is the accumulation time. So how much time it takes for the accumulation or deposition of the metal on mercury to form that amalgam. Then we have cathodic stripping, the same things will happen, and here we have, it is written, it is used for the determination of anion that form insoluble mercury 1 salt at the mercury surface, or insoluble silver salt on a silver electrode. So here what happened, the anion plays a vital role, and the anionic stripping voltammetry, cathode plays a vital role. So here the mercury electrode, the anion from the electroactive analyte gets react with mercury metal to form the mercurous chloride salt, and the same thing, the stripping happen in the second step, and this mercurous salt again accept electron to give the chloride ion, as well as the mercury gets detached. So the second step, in the second step we will determine, or we will have the current measurement in at constant potential. So some halides analyzed in this method are halides like chloride, bromide, iodide, sulfides, mercaptans. These things also can be carried out through cathodic stripping voltammetry. Then the last one, that is adsorptive. Adsorptive means this is a phenomenon of adsorption, that is surface phenomenon, where some analytes get adsorbed on the surface of the adsorbent, and the adsorbed analyte are also known as the adsorbates. So in this technique, analyte is adsorbed on the electrode surface. If it is mercury, then copper gets adsorbed, and there is no electrolysis step. So there is no electrolysis step here, and after completion, deposition of the potential is scanned in anodic as well as cathodic direction, depending on whether the analyte is oxidized or in a reduced form. So the first step is the adsorption. The deposition step in this method amounts to an electrochemical of the pre-concentration of the analyte. The concentration of the analyte on the surface of the microelectrode is greater than the bulk solution. Hence, this is extremely sensitive, and detection limit can be improved by factor of 10 by 6 for selected species. So, in this method, what happens? The phenomenon of adsorption is carried out. So, there will be no electrolysis step, that ions will move and get settled on a particular electrode. This phenomenon is not supposed to be happen here. Here the simple surface phenomenon of adsorption is carried out, where the analyte gets adsorbed on the surface of the electrode, and the second part is same, that is stripping or removal of the analyte, and in the second step the current at constant potential is determined. So at the end we have alternating current methods. So these are all direct current methods. We have AC methods. In this technique, the linear potential is modulated. So modulated by a sine wave voltage of a small amplitude. This produces an AC whose size is determined by the direct potential applied and which is greatest at the half wave potential. So experimentally it is seen that when the potential rises with current, but when at halfway potential, the current is maximum. Okay, so halfway potential, the current is maximum. So the plot of selectively measured AC against the alternative current against the potential, a peak step alternative current polarogram is given here, and the equation is ip equal to kn square ef square into ca, where k is constant, ip is peak current, e is the amplitude, and f is frequency, ca is the concentration. These things are here. Then the height of the alternative current polarization peak is determined the concentration of the analyte, similar to direct current polarization method. And AC polarization peak currents are widely dependent on kinetic or dynamic charge transfer reaction. Then the half width of the peak, this is the half width of the peak, that is P half equal to 90 by n millivolt depending on the electron exchange, and AC polar determination limited sensitivity of electron minus 5 mole per liter because of higher capacitance current contribution. So these are all just electrical things, and just you just go through these things. Okay, and then voltammetric instrument, this is a general instrumentation of voltammetry. Then we have a signal source or linear scan voltage generator here. It will be, this is the cell. Generally we have three types of electrodes are used here. This is a reference electrode, working electrode, and counter electrode. This is counter, this is working, this is the reference electrode, which maintains the constant potential of the system, and it is current to voltage converter here, that is current. Then after that it is computer, in a digital instrument, that is in computer, this converter put a plot, and we will have the recorder at the end. Then we have normal 3 electrode polarized linear scan voltage generator to give different type of signal within working electrode, reference electrode, counter electrode. Then at the end we have the potentiostat allows to impose the potential scanning between the working and reference electrode, while the current flowing through the circuit is recorded between working and auxiliary electrode. Auxiliary means it is the counter electrode, that is the anode. The computer, that is cyclic voltammetry 8 trace analyzer from Metro HM Limited. This is first company, can be used as an integrated instrument with keyboard or a commercially available personal computer interface to measure the system with software can be used. So this is the latest advancement of the voltammetry, to send the scanning parameter to the potential analyzer and check its correctness and accuracy, and handle the current potential output data. So this will be the end of your unit 7, and in the next part we will have a polarogram, that is in our next part. Sorry, so polarography and amperometric titration. So let's have 5-minute break, students, and and after 5 minutes we will have the discussion on polyneuropathy and amplification titration. So at exactly 6:42 I will again rejoin and we will have the class. So till then, thank you.
अक्कर जी आपका नेटवर्क मैसेज कीजिए ना थोड़ा। हेलो अब्रत जी।
हाँ नागेश।
थोड़ा आपका नंबर मैसेज कीजिए ना, मैसेज कर दो ना सर। आपका नंबर नहीं है मेरा व्हाट्सएप लिंक लेने के लिए, व्हाट्सएप करने के लिए
जी
आपके से टेक्स्ट मैसेज। आपका नंबर
नागेश,
व्हाट्सएप
आपको
नंबर
नंबर
मैसेज
नहीं
कर
है?
दीजिए ग्रुप। नहीं है, नहीं आपका नंबर नहीं है मेरे पास। थोड़ा नंबर मैसेज कर दीजिए, मैं आपका टेक्स्ट मैसेज डालता हूँ व्हाट्सएप ग्रुप।
लिखो लिखो, आया?
एक मिनट सर, हाँ बोलिए।
आया नंबर?
एक मिनट मैसेज में देखता हूँ, रुकिए। हाँ 988266, ओके ओके।
हाँ ओके।
ओके टेक्स्ट मैसेज डालता हूँ सर, व्हाट्सएप लिंक भेज दीजिए मेरे को, ठीक है ना।
ओके ओके ओके।
So thank you to all for your kind patience, and let's move on to our next unit, unit 8, related to polarography as well as amperometry. Is it visible, students? This PDF?
No, sir.
Not visible.
Visible, sir. Visible, sir.
I think it is okay
It's
now.
visible, sir.
Okay, thank you, thank you. So this is the next unit, and that is unit 8 related to polarography and amperometry. As I um, uh, already told you that polarography is just a parallel version of your voltammetry, and in amperometric we have study of current. That is that means current is remain fixed at constant current. The change in potential we will measure, and we will have like what are the objectives, what is polarography, then then different type of electrodes, that is DME, limiting and migration current, limiting current, migration current, then diffusion and residual current, attracting diffusion current. These things are there, okay. And we have the concept like E half, that is half the potential, and how the complexing agent like EDTA, ethylene diamine tetraacetate complexing agent, how it can affect the halfway potential, as well as the estimate how we can determine the number of electron exchanged in a particular reaction or in a particular cell. And then we have kinetic current, catalytic current, and absorption wave, followed by polarographic maxima and maximum suppressor. Then at the end we have amperometric titration, further advantages and so on. And then let's move to the objectives. I will not repeat it again. Then we have what is polarography. It was discovered by uh, Jaroslav Herovsky in 1922, for which he was awarded a Nobel Prize in 1952 for developing this technique using dropping mercury electrode. So this is a Nobel Prize level concept, that is polarography. And here the Ilkovic equation is used, that is the diffusion current equation, and complexing agents like EDTA with the zinc, for zinc determination, EDTA complexing agent can be used for complexometric titration. Then we have the same concept, that is applied potential versus current plot, and here is the plot is just like this, that initially when the potential rises, the current slowly increases, and at one point the current is suddenly increased, and again it remains parallel to the, or remain constant to the applied potential. And this point of sudden increase is known as deposition potential, and these things we will have. Then the same thing, the zinc is reduced and gets deposited on mercury electrode, that is calomel electrode, okay. Then it will form zinc mercury amalgam. And then we have the Nernst equation is also applied for these things. And if I applied a Nernst equation to this thing, and if I put positive sign here, here it is positive sign, that means it is reactant by product, and if it is negative, then product by reactant. So as this is represent in positive version of your Nernst equation, so here E cell, it is equal to E0, it is the standard reduction potential of zinc, that is equal to minus 0.76 volt, plus 0.0591 by 2, because 2 is the number of electron transfer here. It is 2. Log, it is reactant by product. So reactant is zinc 2 plus N concentration divided by zinc. So as I already told you that any element or metal is in elementary or solid state or in pure state, if the concentration is taken as 1 molar, so that's why it is divided by 1. So the Nernst equation becomes this one, 0.0591 by 2 log zinc 2 plus N concentration. Then the let's have some knowledge on the electrodes, that is dropping mercury electrode. What are the advantages, how it is looks like, what are the internal parts and what are the different dimensions and everything. The small polarizable electrode, which produced by passing a stream of mercury through a resistance glass capillary. So it is, the apparatus is glass capillary through which a stream of mercury is passed. Okay, having fine bore of 0.05 to 0.08 millimeter with internal diameter of 5 to 9 centimeter long, and internal diameter and 5 to 9 centimeter long. It is a capillary tube. The drop falls at a steady rate of 3 to 5 seconds per drop. So for each drop, it will take 3 to 5 seconds, and adjusted under the head of 40 to 60 centimeter of mercury. Okay. The current oscillates between non-zero value as drop falls from capillary to maximum value as the surface area of the neuron of increases. So this is the instrumentation or the making of dropping mercury electrode, a DMA. This is a very common electrode which is used as the reference electrode in many cells. What are the advantages? Its surface area can be reducible with capillary, even capillary, reproducible. The constant renewal of the electrode surface eliminates passive or poisoning effect. The large hydrogen overpotential on mercury renders possible the deposition of the substance difficult to reduce, such as aluminum ion and manganese ion. Like overpotential or overvoltage, we have already studied in yesterday's class that due to polarization, the linearity of the plot will not maintain and it will deviate from its path, and this deviation is known as happening due to the excess potential or the over potential arises when when um, when applied current or applied electricity exceed the limiting current. Mercury forms amalgam with many metals. This is very important because with many metal of mercury forms stable amalgams. That is just a complex with the metal. The diffusion current assumes a steady value immediately and is reproducible. The surface area of the electrode can be calculated from the weight of the drops. This is the reverse calculation can be made. So the migration and limiting current will be there. There will be two types of current: migration current and limiting current. The limiting current, the first one, is obtained with the dropping mercury electrode is caused by the extreme state of concentration polarization, which result from the depletion of the concentration of the electrode reducible or electro-oxidizable substance at the electrode surface by electrode reaction. So the limiting current concept arises when there is concentration polarization. So when concentration polarization will occur, when the oxidation or the reduction reaction happen, there will be change in concentration. This change in concentration is treated as the concentration polarization. So when the change in concentration is happen, then what happen? There will be limiting current concept will be there. So limiting current is a diffusive force proportional to concentration. So this is directly proportional to concentration gradient, that is concentration per volume. An electrical force, this is a diffusive force that related to your diffusion, and there is electrical force that is the external electricity, which is proportional to electrical potential difference between surface and the solution. So this is the electrical potential difference that is in volt between the surface of the electrolyte and the solution. And so the limiting current is regarded as the sum of diffusion current and migration current. So it is the sum of both of these two. So what is migration current? The migration current is due to migration of ions, which is proportional to electrical potential gradient, that is potential per concentration or per unit area, per unit area at the electrode due to attraction. So here the migration current Im equal to Ti into Ii, where the Ti is the time and IL is the limiting current, right? So we have one table is here, that is potassium nitrate concentration. This is transference number of lead. What is transference number? It is the percentage of current carried by each ion of an analyte solution. If it is lead nitrate, that means the percentage of current carried by lead is known as transference number of lead, and the percentage current carried by nitrate ion will be the transference number of nitrate. So this is in this table only the transference number of lead ion is given here with the change in concentration of the potassium nitrate. Okay, so potassium nitrate is a supporting electrolyte, or this is the salt bridge, you can say. In this cell, it is acts as the salt bridge, that is the supporting electrolyte, and 0.0004% sodium methyl lead maximum suppressor. So this is in addition to potassium nitrate. And what is the limiting current here in microampere, and these are the readings. Then we have diffusion and residual current here. What is diffusion? The presence of excess supporting electrolyte. The electrical force on the reducible or oxidizable ion is nullified, and thereof the limiting current is solely a diffusion current. So when excess supporting electrolyte means this is the salt bridge. When in the presence of excess salt bridge concentration, that is potassium nitrate, the electrical force on the either side ion is nullified, and therefore the limiting current is solely a diffusion current. So now what happened? There will be, and neutralization is maintained on either side of the cell due to presence of this supporting electrolyte or salt bridge. So in 1934, Ilkovic introduced a theoretical equation, that is ID equal to 607 ID equal to 607 NC d to the power half m2 by 3 t1 by 6. This is the equation, very famous equation in electrochemistry, that is diffusion current is due to presence of excess supporting electrolyte, that is the salt bridge, that when the electrical force on the either side of the cell is nullified due to neutralization of the system. So these are the factors with their as usual nomenclature, that the ID is the diffusion current, N is the number of electrons, C is concentration, D is diffusion coefficient, M is the rate of flow of mercury, and T is the dropping time of mercury. Then followed by our residual current. Even in the absence of electroactive substance in the solution having only supporting electrolyte, a small current is always present. This is known as the residual current. If the electroactive substance is absent, there will be no electroactive substance, still the system has some current due to presence of that salt bridge or supporting electrolyte. So this is known as the residual current. So the first is reduction of trace impurity, that is Faraday current, present in the large concentration of supporting electrolyte used. These include dissolved oxygen, traces of metal such as ferric, lead, arsenic. Out of these, DO can be removed, passing pure nitrogen. So these things are there, that due to presence of impurities, Faraday current is there, and it is symbolized as IF in our voltammetry part. And the second source is charging current or capacitive current, which is non-Faradic and is present whenever the working electrode potential changes. So these things are responsible for your residual current. So this current generated when there is absence of electroactivity, that is the analyte, electroanalyte. Then we have what are the factors that affect the diffusion current. One is the main one is the concentration. So diffusion current is when there is excess supporting electrolyte is there, that is the salt bridge concentration, that is potassium nitrate. So remember these things, okay? Potassium nitrate is generally used as the supporting electrolyte or salt bridge in agar-agar medium. Then we have from the Covic equation, diffusion current and proportional to concentration. So it is K equal to ID by C. Then the next part will be capillary characteristics and factor amplitude. What are the capillary factor is there for the current measurement? So as from the Covic equation, we see that the diffusion current depend on the rate as well as the time, and they are therefore affected by their variation. M is directly proportional and T is inversely proportional, because T to the power 1 by 6 is there, so this is inversely proportional to the net pressure of the mercury drop. So here it is written M to the power 2 by 3 and T to the power 1 by 6 is proportional to root over of H corrosion and ID. Then ID by root over of is equal to K, and just go through these things, and at the end we have ID by root over of H equal to K dash. K dash is another constant. These are H equal to Planck's constant, K is another constant, M is the rate flow, T is the time in second, N is the number of electron transfer, D is the diffusion coefficient. So these things are there, okay? So we have mercury in centimeter, height of mercury in centimeter, and this is it is H, here it is the height, this is the milligram per second, this is the rate, this is a second, this is mt into mg multiplication. Then we have height of the corrosion in centimeter. Then the another factor, that is temperature. It is also change in temperature affect all the values of Covic equation except the value of n, because n is constant and independent of the other factors. Then temperature coefficient of M is about plus 0.27% per degree. This is known as the temperature coefficient. So in in chemical kinetics, it is a general phenomenon that when temperature rises by 10 degrees centigrade, if temperature is increased by 10 degrees centigrade, the rate of a chemical reaction becomes double. So this is known as the temperature coefficient in rate of a reaction, that is in chemical kinetics. But in electrochemistry, for diffusion coefficient or diffusion current, the temperature coefficient when the rate is increased by 0.27% per degree per degree change in temperature. And so the temperature coefficient M to the 2 by 3, T to the power 1 by 6 is about 0.5%. So next will be the solvent and the supporting electrolyte. On this part, the diffusion current decreases with increasing viscosity of the solution as D inverse proportional to viscosity N of the medium, and according to the equation ideal constant to N equals 1 to 2, and the change in composition of the supporting electrolyte by adding complex cyclic like EDTA to the electrolyte solution changes the size of the metal complex, therefore D of the ion therefore decreases. So when the size decreases, the movement or the flow rate, that is M, will decrease, so ID will be decreased. Okay, and this will shift to more negative potential, that is half the potential will shift towards left. So it is necessary to keep the concentration of every constituent supporting electrolyte constant within about plus or minus 10%. Then we have some polarographic equations. Then again it is again non-stick equation, E equal to E0 plus RT by N from, if it is plus, it is reactant byproduct, so activity or concentration of oxidant divided by concentration of reductant. This is 0 at standard state. Then we have diffusion current, I equal to Ki OX minus OXO, and we have K1 equal to this much equation. Then we have I equal to Ki of equal to ID. So by combining these two, we have OX at standard state equal to ID minus I by K1. Similarly for reduction, we have I equal to K2 reduction rho, and at the end we have, we will replace reduction by I and oxidation by oxidant by ID minus I. So we have the equation E equal to E0 minus 0.0591 by N log K1 by K2 is the constant minus 0.059 by N log I by ID minus I. So if I go for then it is written here, when the potential of the dropping electrode is equal to half the potential, then I becomes ID by 2. So I becomes ID by 2. So this is ID by 2, this is ID by 2. So ID minus ID by 2, ID by 2. So this becomes log 1. So log 1 becomes 0. That is, this part gets cancelled from this 0.059 by N log I by ID I. So this is a boundary condition we have applied for in halfway potential condition. What happens? I becomes ID by 2. So this cancel. So we have E equal to E0 minus 0.0591 by N log K1 by K2. So now 8.11 equation can be written as E equal to E half minus 0.0591 by N log I by ID I, because here we replaced in 8.11 we replaced the E0 0.0591 log K1 by K2, this part E0 0.0591 K1 by K2 by E half. So this from this to this it becomes E half. So E half minus 0.0591 by N log I by ID minus I. This will be the final equation. Okay. So this is the equation for your polarographic method. That is E equal to E half, that is halfway potential, minus 0.0591 by N log I by ID minus I, and this equation is deduced from applying a boundary condition or a situation that is at halfway potential E half, I becomes ID by 2. Okay. Then how halfway potential affect the complexing agent. So when complexing agents like EDTA is complexed with the analyte, compressed with the analyte. Then size of the analyte increases. So when size increases, the kinetic energy or the movement of the ion will reduce or decreases. So the potential will be decreased. So the electroactive material in polar graphite characterized by half-wave potential. Under any defined set of experimental conditions, each substance has its own characteristics EF, and this is the basis of qualitative polarographic analysis. The half-wave potential is defined as the potential at which the current due to reduction or oxidation of substance responsible for the wave is half as large as the platinum. So as large as this plateau, the half, whether it is oxidation or reduction, this is whether it is oxidation or reduction, the halfway of the potential is known as halfway potential. So effect of complex agents, I already highlighted that this is the complexity part, and this is MHP, charge, and these are the dissociation of metal ion, which is gets amalgamated mercury, and we have reaction. This is the equation. We have equal to E0 plus 0.0591 by n log k instability by minus 0.0591 by log x b minus, and just we have some deductions, say from some like here is the sample and here is the instability ion. Then we have versus standard caliber electrode and log x concentration of the complexing part, and we have this one, that is the half-wave potential value of Q metal ion in complexing as well as non-complexing medium in DME. This is the non-complexing medium and this is the complexing medium with HCl, KCN and ammonium chloride medium, and these are the half-wave potential values. So determination of N means the number of electron transfer or exchange, and how this reversibility of a reaction is happen, and this is the reaction. Then we have at E1 by 4, that means half wave again becomes half. This is E1 by 4 for reversible cathodic wave. We have E1 by 4 equal to E1 by 2 minus this log ID by 4 by ID minus ID by 4, because just recall for half wave potential ID equal to ID by 2, for 1 by 4 it is ID by 4 here, so this becomes 1 by 3. Similarly for E3 by 4 it becomes log 3, it becomes 1 log 1 by 3, it becomes log 3. So if I subtract E3 by 4 minus E1 by 4, then we have 0.0564 by n minus. So therefore the value of E3 by 4 minus E1 by 4 is equal to minus 56 by n millivolt. So this is multiplied by 1000 for reversible anodic wave and is equivalent to plus 56 by 4n millivolt. So if it is reversible, this the sign also reverse, this becomes positive. So for irreversible reaction, what happened? This will be E equal to E half this much by alpha n, that is number of electron alpha log I by ID minus. Now this is just by following the Nernst equation and Ilkovic equation. Then current other than diffusion current, we have kinetic current. That is related to your movement of the ions, and this will be equal to I kinetic equal to 493 n. This is very much long equation, and d 1 by 2 cy m2 by 3 t2 by 3 kf by kb to power half. Then we have catalytic current, that is in presence of catalyst. One redox reaction will carried out, and here the electroactive substance oxidant gain electron to have the reductant, and if the solution contain another substance Z, that is the catalyst, and which is not electroactive and reduces at more negative potential than oxidant, it may catalyze the back reaction like this. If it is present, then the reductant again converted to oxidant, then we have the equation IC equal to this type. Okay, that is 493 n d0 half CO m2 by 3 t2 by 3 k plus kb cz 0, then whole to the power 1 by 2. Then your adsorption wave are there, where surface adsorption is carried out. This type of polarograms we will have in 0.2 molar ammonium chloride pH 6.5. Then it is A is your plus 1 by 2 micromolar sodium propyl xanthate. This is the adsorption took place. Then we have for adsorption current, we have 13.66 Nm 2 by 3 T minus 1 by 3 divided by A. A is the surface area. Then we have polarography maximum minimum suppressors. Then how some agents acts as suppressor, which uh, affects the maxima of the polarogram. The current voltage curve obtained with electro-reducible ion at dropping mercury electrode and is distorted by increasing the current beyond diffusion current. And we have the polarogram, that is diffusion volt versus your standard calomel electrode. That is A is the absence of maximum suppressor A, and B is the after addition of 0.0002% sodium methyl. So this is acts as the suppression. By adding the suppressor, the your potential downs. So these things are here. Then qualitative and quantitative polarographic analysis. We have this part also, that is qualitatively we may predict which type of ions are present, and quantitatively we may determine in how much quantity it is present. Okay. Then we have the next part is these are in different suppressor electrolytes. Okay, ammonia, ammonium chloride, acetic acid, and ammonium acetate, potassium chloride, lithium chloride. This is tetramethyl. It is tetramethyl amine chloride, ammonium chloride. These things are there. Then followed by your qualitative polarity analysis. We have a precipitation of 1 by example is lead zinc mixture, then complexation. So two types of complexing part will be there. That is the precipitation, like silver chloride. We have lead and zinc mixture, and we have complexation with complexing agents like EDTA. Then wave height, just go through these things. Internal standard method of standard addition. Then how the instrumentation of polarogram here. For instrumentation we have mercury column here, constant head mercury reservoir here, and this is the mercury capillary tube. for escape of nitrogen, and nitrogen is for maintaining the inert atmosphere. Then the surface that is upper plug containing potassium nitrate, and this is the sample electrode, that is SCE, and these are the circuit diagrams. And this is the Herovsky apparatus, which for which he awarded Nobel Prize in 1952. Then we have amperometric titration, just like this. We have current versus amount of reagent added, because this is titration means this is addition of the titrant, right? So if so this will also follow your Ilkovic equation. The electroactive material in the solution will by interaction with other reagents like EDTA. Like if I go for zinc determination, we will add EDTA, and the zinc ions will make complex with EDTA, and as the complex is formed, the current downs because the number of ions will decrease, and this will and there will be a decrease in current with addition of the reagent, and by extrapolation of that plot we will have the endpoint, that at what point the total zinc ion will be consumed by the EDTA. Similarly, these type of curves are here. Just I am read out this one from A to D. Common type of curve of amperometric titration, and A dash and D dash polargram of individual substance. Yes, and so in the left hand side we have the amperometric titration, and the right hand side we have polarogram, that is applied voltage versus current. So this is just a titration. Okay, then we have the titration cell is just like this. This is amperometric cell, and this is just a polarograph unit. Like your cell, there are 3 electrodes which is connected to a circuit, and followed by one recorder. Then one monitor is here, computer is attached. Then, but in a amperometric titration, Pyrex glass system is used, which have thin-necked, flat bottom is there to make it strongly stand into the micro burettes are here. Dropping mercury electrode is here. Gas outlet tube for nitrogen, with an additional inlet of nitrogen provision is there, and this is the burette. Okay, this is the addition of EDTA, complexing reagent. So if addition of EDTA will be through this burette, what happens, the zinc 2 plus ion in this solution gets complex with the EDTA, and gradually the number of ion will decrease, and when the number of ion will decrease, there will be the current will decrease. Though, so by noting the current with addition of the EDTA, we will have the endpoint. So what are the advantages? Carried out quickly, that potentiometric or visual indicator method are unsatisfactory. When in so the number of applications carried out at a migration current. The resultant of the titration independent characteristic of capillary. The temperature need not to be known provided it is kept constant. Graph is convenient as a mean of applying the voltage to the cell. It is not essential in amperometric titration. Okay, so voltage is not required. So few example of amperometric titration is zinc ion. This is an example, zinc with EDTA. So we must have a chemical like 0.005 molar zinc, 0.01 molar EDTA, in cyclohydroxyamine. Then so these are the steps how to do the empireumatic titration. Then we have second determination of sulfate with lead nitrate. So lead nitrate will convert sulfate to lead sulfate. So gradually the concentration of sulfate in the medium will decrease. So the current will decrease, and we will have, by extrapolation we will have the end point. And this is the reaction that in potassium sulfate is this analyte, the electroactive analyte, and lead nitrate is the complexing agent. So here what happened, the sulfate react with lead 2 plus to give lead sulfate, and this will decrease the concentration of sulfate in the medium. Then we have determination of lead with standard dichromate. This is dichromate means this is uh, K2Cr2O7 potassium dichromate with lead. So lead will react with dichromate, potassium dichromate to convert it to lead dichromate. Okay, then the same process is adopted, and we will have the current. Titration with the rotating platinum electrode. So here steering is there, rotation is there. The constant steering will be there, rotating platinum electrode. So this is the width, this is the copper wire, this is the mercury, this is again the copper wire, then here there is platinum wire. Then determination of antimony with potassium bromide. Just read these things, this is very much similar. Then by amperometry or dead stop endpoint method. This is biamperometric instrument where two electrodes are used. One galvanometer is there, and this is a circuit diagram. When the volume of the reagent is added with respect to the current, we have two types of plots are here. If both couple involved in titration reversible, that means here two ions are estimated. Okay, that is iron as well as cerium. Then this is, so that is the biamperometry. Then we have and this I think is the last part, and we have the same thing for your iodine and thiosulfate. Titration of iodine by thiosulfate. In this iodine couple is reversible, and titration of thiosulfate tetracyanide couple is irreversible. So these things you just read and you will understand it clearly. So to remember these things, it is very much a hard work, or you should be so much dedicated that you are able to remember lots of information for your theory. And you just I will suggest you to uh, make your own note, and just try to remember the equations one by one, and the terminologies have their usual meaning, and we will have the different type of electroanalytical methods. Actually these things we will also not studied in our BSc and MSc level, and also in MPhil and PhD level we also did not read so much of things that IGNO study material have. So these materials are very good, and a thorough understanding and thorough reading is required uh, to have a broad knowledge on this. And as we are not yeah, working in this field, so that's why it is not, and also within 2 hours it is not possible to cover so much things in of 2 units. This is a very much tedious work. So at the end we will cover today we are able to cover 2 units 7 and 8, and in the next class, that is tomorrow, and we will have unit 9 and 10, and you have 13 units in this paper. So hopefully we will cover all the units in 7 days. And if you have any doubt or anything else you wish to say, over to you, students. And I hope this is the new things for you all, because I will also prepare. I will also have uh, preparation of 2 days, 1 to 2 days required for each unit cover for your class. And it is over to you now. If you have anything to say or any question, I will try to answer it out. Uh, so we have 5 minutes so for discussion, and then after we will wind up. So over to you, students. And do not worry, I will share all the PPTs like our second paper at the end of the this paper, completion of this paper. So about the PPTs, so do not worry. And as discussed yesterday, your practical classes will be held just after the end of the theory papers. And you have, I think, three practical papers. Three, not three. This is four. Four practical papers are there. And Bhubaneswar, I think IGNOU Bhubaneswar will conduct all the practical classes
Sir,
for this session.
sir, hello.
Yes, Abra. Yes, yes.
Sir, practicals are held in online classes.
Yes, 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 yes. It will be online because it is not possible to have one common practical lab for you all, because
Yes,
you
sir.
all are belonging
Yes, sir.
to
Yes, sir.
different. Okay.
Yes, sir.
So it
Sir,
will be online. And from each paper we will discuss 2 to 3 experiments, and from that only you will have the practical examination. Okay.
yes, sir. Sir, how much will start in practical classes?
It is again of, I think it is of again 2 hours for each paper. That means for discussion
Sir,
of
in which date? मैंने कहा in which date?
the dates are not fixed yet, but we will have a rough discussion that after theory class you will have the practical. Okay.
Okay, sir. Okay, sir.
Okay, so thank you to all for your patience hearing, and hope this cooperation will continue. And from my side and from Regional Center IGNO, I thank you to all for your kind cooperation and participation, and hope this participation uh, will go on. So thank you to all.
Thank,
Thank
We will
you, sir.
have
Thank
okay.
you.
We will
thank you,
have
sir. Thank you,
okay.
sir.
Thank
Thank
you.
you, sir.
Thank you.
Thank
Thank
you.
you. Thank you. Thank you. Thank you.
Thank you, sir.